Swayam Prabha. Digital India. Educated India.
Good morning. If you recall, in the last class we talked about the 4+2 cycloaddition, right, in the heterocyclic chemistry, and very briefly, if you review what we exclusively did in the last class, that cycloaddition of the furan moiety in most cases, and the scope of the reaction is somewhat limited to special kind of substrates or dinophiles. We have seen that if it is a furan molecule, the dinophile must be pretty active, like alkyne, alkynyl, or allynyl type of molecules, or else if the dinophile is little less active, you have to make the other part more active. Like if you have a, let us say, double bonded compound, so you have to have benzoisofuran, where this furan moiety is little more active. For rest of the cases, like if you have a double bonded electrophile like malic anhydride, the reaction takes place for simple compound without any problem, because malic anhydride is considered to be a very reactive dinophile. But again, in the synthesis of cantharidin, you have seen that this Diels-Solder is not that easy, but that sort of problem can be alleviated by either using high pressure or Lewis acid. Okay. And but in the case of the intramolecular reaction, the situation is a little different. Even if the dinophile is just simply a carbon-carbon double bond, that would also be active, but it is somewhat like so the reaction takes place without any smoke. Then we went to these important other things, that is synthesis of pyridine means diatomic compounds. There is oxazole. Okay, that was the given, and you have to do a small correction. The last time, if you recall, we began with a oxazole derivative, and which you can consider to be an furan analog, and where the oxazole can undergo Diels-Solder type reactions or 4+2 cycloaddition reaction, and eventually it gives a pyridine nucleus. The structure was wrong the last time. Actually, the ester should be in 3 and 4 positions rather, and this OH is 4 and 5 position, and OH is in 3 position, and then there is the hydrogen up here, and so intermediate, just do a small correction. Last time also we did this, we missed one nitrogen. So, the nitrogen should have been in the position here, and then as usual this ester here and ester here, and this is the O ethoxy, and the catalyst was neodymium triplet. So, what it means, that if you have a double bonded kind of dinophile, the reactions could be little sluggish. And then also we talked about this is isoxazole. How do we make isoxazole? Isoxazoles are made by cyclocondensation of the corresponding compounds. The way one can do it, just actually this sort of you start from this NaH, and then what this is basically formamide. It's a formamide, and then you have to have a ester group and oxygen and ethyl, right. So, if you see and this one can be this is nothing but it is something derived from corresponding amino acid. Amino acid will have a carbon, a carboxylate, and this amino group in the same carbon. So, if you functionalize this NH to group of amino acids and or formulations, or else I mean one can also do let us say acyl chloride. So, if you can take this acyl chloride kind of thing, and so you can get to the this molecule, for example, let us say R1, and so you can get to this sort of compounds. Okay. But only problem is the problem if the cyclodehydration, how do you do it? How do you do it? Okay. So, essentially you have to have a dehydrating agent. One of the dehydrating agent, commonest dehydrating agent what we said is PPA, polyphosphoric acid. How do you make polyphosphoric acid? Polyphosphoric acid it is made out of phosphoric acid. What else? Vogel's book, P2O5. So, basically you have to remove some more water and then also, and then you have to do the condensation sort of okay. So, it is a nice way of doing it. In other possible, there are plenty of dehydrating agent, all of you know, right. One of sulfuric acid is commonest one, DCC also is there, DCC, but this is not very effective in this case. Alternatively, other than PPA, is you can go to this sort of compound. One of them is PPA, other I said what Burgess reagent, Burgess reagent. Then I mean you can go on talking about many things, and then the next thing is this is very useful though, and triphenyl phosphine and iodine complex. For triphenyl phosphine and iodine complex, especially this is very useful for oxazole sort of compounds. Okay. I mean one can go on talking about any other possible, but these are the reagents which have proven to be very effective in the formation of the isoxazole. So, okay, that means formation of isoxazole is not that tough, but if you have the right choice of the dehydrating agent. And I told you to go through Burgess reagent. How many of you just typed Burgess reagent in Google? Nobody. Nobody. That's kind of bad. Okay. How many of you have heard of Monilal Bhaumik, Dr. Monilal Bhaumik? Big hand. I want to see big hand, because yesterday in my lab I asked, but nobody knew that. Okay. So, so similarly, I mean, okay. Burgess reagent, last time I told you. Okay. It's a very simple reagent though. It is made from chloroisocyanate, okay, chloroisocyanate, and then chlorosulfonyl isocyanate, chlorosulfonyl isocyanate. If you close and add methanol, and then add I think first you have to add triethylamine and then methanol. What you will see actually sulfone part is intact, the chloride is removed. So, you get a quaternary nitrogen here, and then NCO, and that goes to so N plus, so then goes to this is methanol. Methanol adds to this carbonyl, right, and so you get a carbon ion. So, essentially this is kind of a salt plus nitrogen and a minus nitrogen. This is actually Burgess reagent. This is easily prepared from just commercially available. This is all these materials are commercially available. This is one of the nicest dehydrating agent, very nice mild kind of a dehydrating agent. The mechanistically these reactions also gives the olefin in a cis elimination fashion. That means and primarily works for secondary and tertiary, okay. Like any most of the dehydrating agents are very useful for secondary and tertiary. In case of primary, etherification takes place, right, and then we will come back to that. Okay. Any other reagent available for dehydration of alcohol known to you other than sulfuric acid though? Do not talk about sulfuric acid. Mild, sort of a mild dehydrating agent. Mild dehydrating, even this sort of compound like carbon tetrachloride and triphenyl phosphates. If you have a diol, 1,3-diol, let us say, you can just do this cycloetherification. So, cyclization can take place by cyclodehydration. So, it is similar to triphenyl phosphine iodine. Triphenyl phosphine iodine means you have this one, this phosphonium plus and iodine minus, right. So, carbon tetrachloride and triphenyl phosphine is exactly same equivalent to this. Some name reaction it is, right. What is the name reaction? Apple reaction, something like that. Okay. So, that is equivalent actually in situ the reaction produces this sort of species. So, whenever you have a sort of a phosphonium kind of salt, you can here you have an ammonium salt, and let us say you want to do a dehydration kind of thing. So, so what is expected here, this alcohol part would displace the amine. So, what you will see, then sulfone is there, right, then O and this R, and then you have a hydrogen up here, right, and then N, this is minus sort of a carbamide moiety, and this. So, what next? So, basically, you will have this intramolecular kind of hydrogen transfer or abstraction, and then you have a beta elimination process, and the sulfonate comes out, and eventually what you get is like this R here, and this elimination of oxygen and hydrogen actually takes place in cis fashion, syn elimination. So, exactly same thing happens here, and but this in this case the activation actually of NH is done by this, and eventually if you look at this mechanism, if you go this way, then eventually this water is eliminated. So, that means if you have a cyclic ketal or hemiacetal kind of thing, that would undergo elimination to provide the corresponding oxazole derivative. So, this is one way of doing it. Then this is very similar fashion. If you have an oxazole, but they just change the reacting partner, for example, to malic anhydride, the reactions proceeds very smoothly. And then take an example of the intramolecular version and again oxazole. So, oxazole means 1,3 heteroatom, and then if you have a system where now you have a double bonded compound, double bonded dienophile like the previous ester, but it is a little active, more active again by the presence of one more electron withdrawing group, and then you have all kinds of this functionalization. In this case is a tertiary alcohol and corresponding the silyl protected group, and the reaction. So, what is the product? That means one of that means basically by giving you this example, I mean to demonstrate that these sort of reactions are very useful for constructing pyridine nucleus with multiple substitutions. What you will see, and then the reaction, of course, the reaction conditions are often just heat, and so what is the product. So, I think all of you can work out the product, right. So, the way I have written, so it looks like it is a Diels-Alder intermolecular Diels-Alder reaction, right, intermolecular Diels-Alder reaction. So, you can put here, and then so double bond here, and this and this is ester, and then alpha to this is a this is a ketone, this is a ketone, and then you have this and this oxygen, and this is a silyl group, and the double bond will up here. What next? What next? Is there any chance that of the retro Diels-Alder? That is what you have to keep in mind. Is there any possibility of retro Diels-Alder? So, that means Alder-Rickert reaction. Whenever you are doing thermal reactions, you have to okay. Just by looking at the structure, you have to be able to predict that. Then only you can write the final product. So, is there any possibility of Rickert reaction? Means retro Diels-Alder reaction. Retro Diels-Alder reaction. See, what you have to look for retro Diels-Alder reaction, you have to have a 6-membered ring. So, be it a carbocycle, be it a heteroaromatic, or sorry, heterocyclic. So, you have to have a 6-membered and a double bond or multiple bond, triple bond. So, I see a 6-membered ring and it contains a double bond. If you see the Diels-Alder reactions, basically that means there is a retro Diels-Alder possible, but it will go back to the starting material. No new product would come. That means okay. That means then what is the other possibility under these conditions? You have an eliminate product hydrogen that can undergo elimination, right. So, sometimes this thermal elimination is very favored if the aromatization is one of the driving force. Okay. So, you have this oxygen, or else you can this is another way of looking at, or else you can look at this way, that you have a or you can write is E. I think this one would be the preferred pathway. Oxygen up here, this is E, and this is a 5-membered ring with a ketone, and the adjacent group is oxygen and silicon, and there is a normally this hydrogen has a propensity to expel the oxygen, right. So, there is a possibility that it would first form this sort of thing, and then eventually it will undergo aromatization. So, you can although it was somewhat strained, but you can just go on writing this is E, this is oxygen minus, and then you have all other thing, and then the hydrogen can undergo dislocation, right, to OH, then E, and then you will have minus here, and in the meanwhile this hydrogen, sorry, I think mistake there, okay, this is one nitrogen, okay. So, plus, so this hydrogen now undergoes its elimination, this may be undergoing elimination. So, eventually through all the steps you are going to get what you get is a pyridine nucleus, and what else? You have a 5-membered ring. On one side you have the ketone, other side you have the silicon substituent and the methyl substituent. Okay. And then 1, 2, this should be the 3 position. 3 position is occupied by an ester group. That's it. So, as a whole, what is the lesson we learned? That oxazoles are very nice dienophile in case of this dienophile, sorry, diene, and they undergo nice Diels-Alder reactions, and end result is that the construction of pyridine, and as you can see here you have a bicyclic pyridine nucleus, and the substituents are as it is. Then we will go to, that means so far we have somewhat like a standard kind of Diels-Alder reactions, okay, and in only one case last time we saw an inverse electron demand Diels-Alder reactions. So, where do we see the inverse electron demand Diels-Alder reaction? Okay. What are the inverse electron demand Diels-Alder reactions? That means the diene part should be electron deficient. So, when do you see a diene part is electron deficient? Under what circumstances? No, diene is electron deficient. How do you make the diene electron deficient? The standard way is to put so many electron withdrawing groups. That is the standard way of making a diene electron deficient compared to the normal structures, parent structures, right. What are the other mechanism by which one can make the diene electron deficient? Yes, fine. So, if you have a substrate having an atom which can undergo coordination with electron deficient, that is one of the, so essentially yes, you are basically you are making that, that is also an alternative way. Any other way? Any other way? You have a diene system, for example, no, electronically you have to make it electron deficient. In the last class I gave an example, it's a 5-member ring. So, let us say you have a 6-member, for example, you have a diene of this kind, let us say. So, okay, compared to our parent system, for example, butadiene, is it electron deficient? Yes or no? Yes, because you are putting an electron withdrawing atom. So, that is electronegative atom basically, electronegative atom. That means, if you put more number of electronegative atom, the whole diene system, this should be a important diene, okay, and which is electron deficient. And this concept was of course discovered by somebody else, but a scientist named Dale Boger, I do not know, maybe many of you have heard Dale Boger, he is in Scripps Research Institute. He popularized this reaction. So, some people sometimes call Boger's reactions. And what he did, he put as many as 2 nitrogens in the ring system, that means triazine. So, triazine, okay, triazine. So, if that is, this is electron deficient diene, then you have to have electron rich alkene, and electron rich alkene could be, I mean, it is a propyl chain here, and this was one of the earliest example. So, what is this? By looking at, we can say it is an enamine. So, enamine, that means enamine double bond. So, it is an example. So, enamine double bond also participates in a Diels-Alder reaction, provided the reactivity nicely matches. A little high temperature is required. If I recall, it is close to the reaction takes place at around 300 degree centigrade. So, all of us can. Now, the question is see, if you add this, what should be the structure? How do we find out the structure? See, that means these are the 2 carbon atoms, right. So, these 2 carbon atoms, that means it will add to the 1,4 end of a diene system. So, you can take these as a diene system, you can take this as a diene system, you can take, I mean, all any 4 combination of atoms would be a diene system, because the bonds move, right. or not moves, I should say, I mean it can be picturized in any way by because of the resonance. So, that means any 4 bonds component or 4 atom component could be taken as the diene, but where do you see this? Okay, the nicest way to predict this is to first see the because it is an electron inverse demand Diels-Alder reaction. So, look at the dienophile part. So, that means in this case this is this the electron density increases at the beta position of the enamine. Beta, that means this one is electron rich, fine. I mean you do not have to do all sorts of homo-LUMO calculations, just hand waving calculation is perfectly all right. Now, in the triazine which one is electron deficient, that is it. Once you fix the 2 atoms, then the rest are automatically fixed. Which one? Let us say I will give you the numbering 1, 2, 3, 4, 5 and 6. So, which atom is electron deficient in triazine? 3. Okay. Which one? So, why not 6? Why not 6, right? Well, there is a possibility. Actually, 3 and 6 both are equally possible. Arguably, one can say, okay, nitrogen is more electronegative than carbon. So, possibly 3 is more. In fact, that is what is happening. In any case, but for us, and let us see what happens actually. And the reaction takes place at 3. So, that means this N would add to this one. So, how do we write? I think I will write in linear fashion, that would be better. So, this nitrogen here, okay, and then this adds here, then you will have a methyl group, sorry, this nitrogen, then this is that pyrrolidine ring, and you have a propyl chain, and then this is then 1 4, that means 1 2 3 4 now. Now, this portion becomes the diene part. If that is so, then in the middle bonds are the double bond, and this is basically at the moment it is just innocent, it is not taking part, and that is it. That means, if you can rightly identify the most electron deficient atom in the diene part, then it is easier to establish the regiochemical problems and the corresponding regioisomer. And what next? So, now you have to look first of all, yes. So, is it satisfying? Yes. So, if there are 2 double bonds within the 6 member ring, there are 2 ways to retro Diels-Alder, this way and the nitrogen side. Okay. Nitrogen obvious, very obvious. Why? Nitrogen triple bond energy is very high. So, that is it, or but the reaction, if otherwise takes place, it will go back to the starting material. And so, that means okay, we will write the way it is already written, and sorry, this. So that means I think this way it looks better. So, nitrogen comes out, right, and then you will have a double bond, methyl substituent and the propyl substituent and the pyrrolidine ring system, right, but the bonds are not fixed. So, the bond should be fixed here, the bond migrates and this. What next? There is no other conditions, basically. What next? Actually, then there is under thermal conditions. See, aerodation is such a strong driving force. Under thermal condition, it loses the pyrrolidine. So, it loses pyrrolidine. So, eventually what you will get? You will get a pyridine derivative, right? Pyridine derivative with a 3 position, 3 and this propyl chain. So, 3,4 disubstituted pyridine, 3,4 disubstituted pyridine. Okay. So, why is it so important? First of all, so many things to be learned. First is enamine double bond participates, then triazine is an electron deficient system that undergoes Diels-Alder reactions. The ultimate net result is a pyridine derivative. Pyridine derivative is well defined one single isomer and disubstituted pyridine derivative. And it is a very important one, because if you try to just think about alternative synthesis, for any synthesis actually you should start thinking about alternative synthesis. If you can come up with an easier synthesis, that means that synthesis is is not merited. Okay. So, if you have, let us say, synthesis which is more difficult than this, then this one easier synthesis, that means the pyridine derivative, the method is more powerful, that is it. And just for a moment you just think about the alternative way of making a 3-methyl-4-ethyl pyridine. How do you make? Of course, in heterocyclic chemistry, especially in pyridine chemistry, these electrophilic substitutions are very limited, not well defined. So, the best thing is to approach a pyridine molecule by constructing the ring, and obviously the first choice should be the cycloaddition reactions. Okay. And let us look at and see whether you can. There is one more example I have, where you have again a triazine, and now it is triazine, and you have all the three positions are substituted by ester, E actually in ester, fine, and this is pyrrolidinone, and this and N-vinyl pyrrolidinone, I heat it. So, what do you expect? So, you have to first write the intermediate reaction. Okay. So, the way we have been writing from it is easier to make out now. We have already known that okay, triazine is a diene system, electron deficient diene system. So, this should be an electron rich dienophile. Okay. And now you have to see the orientations. So, although you have a carbonyl group here, but this has this is well known, though this nitrogen actually directs these electrons towards the beta positions. Once again, like the enamine case, this reaction takes place on the beta carbon, fine. I mean, assuming that, let us see whether we come up with the right structure. Okay. And now here you have okay, what are the which are the number? Okay, number of okay, so 1 and 2, 3, 4, 5, right? Numbering is wrong, right? This way. One, 2, 3, 4, 5, and 6. Okay. So, this beta carbon should attack one of these carbons there somewhere. Which one? So, that means no, we are saying 1, 2, 3, 4, 5, and 6. So, you have to identify the diene component. In this case, I mean like the previous, previous case, you had identified 3 as the most electron deficient carbon, right? And the diene was 3, 4, 5, 6. In this case also, you can just very quickly, because now we know that nitrogen eventually would eliminate, right, all these reactions. So, you can just ignore the nitrogen part. That means, the rest of the 4 carbon atoms are actually the dienophile. And normally, in most cases, like actually it gives CN-CC component, CN-CC. that means one carbon, nitrogen, carbon and carbon are supplied by the diene part. Even in case of the oxazole also, when you go to the oxazole chemistry, you will see a carbon, nitrogen, carbon, carbon, this order normally is supplied. Now, of course, we can see that 3 is more electron deficient here. So, that means in this case 3, 4, 5, 6 is the diene part. So, let us say whether we are coming at the right or not. That means this part remains as it is, right, and then you will have a double bond this, and which one should be the beta carbon, this one is the beta carbon, then this is the alpha carbon, and then rest is what, E, and then E and E, and now the double bond should be this one, right. So, nitrogen eliminates. So, if that is so, then this one, and this is the pyrrolidine known, and this is E, this is E. So, E and nitrogen eliminates means you will have a diene here, right, and then of course, what else, thermal elimination would eliminate this pyrrolidine. So, once again you are, it is just basically an extension of the previous example, where you will have nitrogen, just it is a pyridine derivative. So, it is a pyridine triester. Okay. So, that means just basically identifying the electron deficient groups atoms, one can just and quickly establish this regiochemistry of this problem. And whenever you are, let us say, wanting to form a CN-CC skeleton or CC component, either you can choose oxazole or you can choose the triazine. Okay. And the other examples, let us say, I think in the last year we gave you, this is now. So, previous example was this triazine, next was triazine, now this is a diazine system. So, diazine system, in this case it is pyrimidine. Now, whether this reaction would undergo Diels-Alder reactions or not. What is your guess? We have seen triazine case. Triazine case, the reactions proceed very nicely. What about this one? Basically, we do not know. At least we do not know that pyridine does not undergo Diels-Alder reaction. Pyridine, does it undergo Diels-Alder reaction? No. Electron deficient pyridine? No. Okay. But we will see towards the end, we will see. We will see in certain way. Okay. That means, in the extreme case we have seen the triazine. That means, if a 6-membered ring with 3 nitrogen is sufficiently electron deficient to behave like a diene system, fine. And now you have a situation. So, what can you do? Actually, if it is an intramolecular, so you all know that either one of these components should be active or more active than the regular ones, or you have to have okay, electron deficiency increased or decreased. In this case, this is a propagyl group, and nitrobenzene as a solvent, and the boiling point of nitrobenzene is around 140 degree centigrade. So, once again, what you see is a nice reaction. The reaction proceeds. I mean, I can write in 2 ways, but say like you can write this way, that double bond, this is the propyl portion, oxygen up here, and then you have 2 methyl group, then on nitrogen here, and one nitrogen and this. Right. So, it is again intermolecular version. How do I write? This is a pretty easy case, because this portion is symmetrically 1. You do not have to just think much about identifying. So, 1, 2, 3, 4, that means this end is reacting here and this end is reacting here, and both are equal and symmetrical. Now, also we see that there is a chance of the retro-Diels-Alder reactions. There are 3 different retro-Diels-Alder, this here, here and here. Okay. Obviously, if the takes place here, it gives the starting material, and both are equivalent. So, if the reaction takes place on this side, it is a minus what? HCN. That means C triple bond N. In previous cases, we had the loss of nitrogen. In this case, we have HCN. So, HCN. So, that is lost. Then what you will see? 1, 2, 3, 4, 5, 6. So, it is again a 6 member, it is a pyridine nucleus, right? Pyridine nucleus, and and 1, 3. So, you will have oxygen and this. So, you will have this. So, pyridine, so furopyridine, pure furopyridine. Okay. And this reaction obviously, many of you by now know that if the methyl groups are there, actually the intramolecular reaction is favored because of Purpey-Gold effect actually. And then very similar reactions also has been tried. Just what happens, like because we have identified this is an electron inverse Diels-Alder reaction, right? Electron inverse Diels-Alder reaction. If you do not have the methyl group, the reaction either does not take place or is very sluggish. So, what you do, let us say you have a situation, sorry, so oxygen, and then again a triple bond, just like the previous one, just without the methyl group, and the substrate is very similar. Normally, the reactions are very sluggish without the methyl groups, because you have only 2 nitrogen, electron deficiency is not that much, and so you have to increase. And but in this case, by putting the substituents within the molecule, means making it in intermolecular versions, you have increased the probability of the reaction. But then removing the methyl groups, the reactivity is decreased. So, what else can you do then to increase the reactivity of the substrate, so that the reaction takes place at lower temperature, and in this particular case the reaction can be carried out at 110 degrees centigrade, What else can you think? That means you have to basically like Abhishek said a few minutes ago, that you have to make it a little electron deficient, that is it, electron deficient, then we have to use Lewis acid. Other than the Lewis acid, actually in this example what they did, they quaternized this nitrogen, that is it, quaternized this nitrogen. And if you do the Diels-Alder, then there is a chance that okay, this quaternized nitrogen would be lost, all HCN would be lost, but in this case the HCN is lost. So, what you get exactly like the way we got it was the puro and puropyridine case, the ethyl group and this. Okay. So what next? We have seen triazine, we have seen diazine, nitrogen, okay, pyridine we will see towards the end, but let us look at an example where you have tetrazine. Actually tetrazine, which is very popular in the heterocyclic chemistry, is a molecule of this kind, a symmetrical one, nitrogen here and this nitrogen and this is ester, and normally let us say it is a methyl. People sometimes call it is a Bogar's reagent, this one, Bogar's reagent. So, what does it do? It is an equivalent to CNC. All other cases we have seen they supply CNCC, right, CNCC, and but this is a case where it provides only CNC. Okay, that means nitrogen would be eliminated, and this reaction is so clean and neat. Just if you let us say if you have a triple bond and a big aryl group and big aryl group here, you do not have to have a very active alkyne group, the reaction nicely takes place. So, just mix them together, just heat, and as usual. So, this portion remains as it is, and nitrogen and this right, and this is E, and then the part of the triple bond, this is here, this is AR and the AR, and then this. Now, in this case, as you can see that retro-Diels-Alder can take place either at this nitrogen pair or this nitrogen pair, does not matter because both are equivalent. So, eventually what you will get, this is AR, and in this case this is E and E, and nitrogen and nitrogen. What is this derivative? 2 nitrogen at 1 2 position. What is the name? 1 3 is pyrimidine. Good, pyridazine, and the 1 4 is pyrazine. So, you get nice pyrazine, tetra substituted pyrazine, that means it is fully substituted pyrazine. And the difficulty in this case, I mean, why such a reaction is very important. Such a reaction is very important because to functionalize the heterocyclics in all carbons is very difficult, because one substitution is no problem. Second substitution ortho position, it creates a lot of steric hindrance, right. Then one more steric hindrance, like here you have a lot of steric hindrance, and the group here normally is bulky, especially in the context of vinyl product synthesis. Okay. So, this is one of the nicest to have. That means, Diels-Alder can circumvent little bit of the steric interactions. What next? That means, tetrazine can be made use in the Diels-Alder reaction to produce pyridazine derivative. That is not all. Actually, once upon a time, I think I told you, it is a very clean reaction. If you react with zinc and acetic acid, you will get something. What is it? It gives actually pyrols. So, pyrol, so this is actually known as Bogar's ring contraction, the same Bogar actually ring contraction. So, eventually what you will get a pyrrole ring. So, AR sorry today something is happening here. Okay, so, and this E and this E, so it is a nice reaction though, and the reagent is very cheap, zinc and acetic acid. So, just simply reduce this and you get a tetrasubstituted pyrrole, and this has been used in synthesizing quite a few natural products. The one that is synthesized, I think just very briefly I will write the structure. It is something like this. It is even little more complex, but you have something like so you have I mean very similar pattern, OH on this side and OH on this side, OH on this side. So, that means so again this is an example of how to make use of these heterocycles, and this is tetrazine. But how do you make this tetrazine? How do you make the tetrazine? Any idea? Any guess? Random guess. Just by looking at the structure. How do you make it? In fact, I was not knowing before. I mean, of course, now I know. Okay, I think we will begin with let us say how do you make this compound? Methyl diazoacetate. Methyl diazoacetate. How do you make? Methyl. Glycine, right. So, methyl ester glycine and sodium nitrate diazotization. In all other cases, diazo compounds are unstable, but if you have an electron withdrawing group or conjugated system, this diazo, that is it. And then if you heat just warm with sodium hydroxide, actually sodium hydroxide, what you will get? You will get this tetrazine, but in the tetrazine and so tetrazine salt and this one, this compound. You can just do little manipulation. Basically, many of you probably know that the CH is sufficiently active, it can be deprotonated by a base, even with LDA or other thing. This can be deprotonated and then undergoes dimerization, okay, or cyclocondensation, you can say. What is to be done next? The next is just as it is thionyl chloride and methanol, and so you will get corresponding methyl ester. Methyl ester here, methyl ester, sorry. So, methyl ester and this NH and NH, and then I think all of us know what to be done. What next? You have to remove these two hydrogens. So, basically you have to do dehydrogenation. So, how do you do? How do you do the dehydrogenation? So, you have to basically look for some of the reagents. Quinone, or quinone would not do the reaction, because all of us know quinone with quinone and NH, that's the those are the limitations. For example, DDQ etc. all are known to undergo rather known to induce the oxidations or dehydrogenations, everything, but when it comes to the nitrogen compounds, then you have some limitations, because nitrogen can undergo Michael addition, nitrogen undergo displacement, all these things are reactions. There is a reactions again in indole synthesis called Nenni-Jetsky reaction. So, Nenni-Jetsky reactions will their nitrogen adds to the quinone nitrogen, sorry, quinone nitrogen adds to the quinone and carbonyl. So, all these things take place, and so you have to have look other normally the palladium carbon is one of the cheapest kind of reagent, but in this case that has been recommended is something like simple nitrous acid that gives you the reaction, that gives you the product. Nitrous acid also is an oxidizing agent, okay, and
diazotine found in that reaction.
Which reaction?
That diazoacetic ester with sodium hydroxide.
Sodium hydroxide.
Is it not the preparation for diazomethane?
But it is not though, I mean obviously it is not, but I am trying to recall. Actually normally they require an amide, normally require an amide, either a sulfonamide or that kind of thing, not an ester, not an ester. So, diazomethane normally I mean like say how do I say, let us say if you have is nitrous like compound of this kind, NH, this sort of compound you have to have. So, this sort of things should be there, and I mean we can go on basically, but it doesn't form though. It doesn't form, that's for sure. I mean the most of the then you get this nitrogen, OH and CH3. Okay. Then further it goes, so you get this one. Once you have these, automatically this OH actually abstract the proton and you get this diazomethane. Okay. So, essentially that means nitrosomethyl urea if you use, then it can undergo. That means, so these are all triple metal. Okay. And then I think we have many other examples probably. I think I will give you one more important reaction very quickly. This is a reaction called, you may have to read little bit by yourself. It is a very useful again. It is known as Bratzer cycloaddition reactions. So long we had talked about, so long we have talked about those pyridazine and these basic pyridazine and triazine, tetraazine, all these things, but we never talked about this pyridine kind of nucleus, but if the pyridine nucleus is part of a bicyclic system. In this case, you will see here you have an aza isoquinoline derivative, and there is a nitrogen, and you first treat this with these dinitrochlorobenzene, and then very interesting reaction though. I don't know whether you should be able to predict the product or not. Then it is an amino alcohol, and just put them in water and heat. So, what is the product do you expect? The product actually, what is happening here, I will just tell you, quaternization of nitrogen. Quaternization of nitrogen, we have seen that before, right, in zinc salt, in the preparation of the zinc salt. So, and once it is quaternized in one side, the other side remains as it is. So, then what? Let us say I will write AR, let us say this is chlorine and AR. What next? Zinc salt undergoes ring opening, if you recall, it undergoes a ring opening. Now, you have substrate here, and between the amino and OH, all of us know which one is more nucleophilic. Amino is more nucleophilic. So, it will undergo nucleophilic all these things opening, and then recyclization. Eventually, what you will get this one. It is a nice reaction, very nice reaction. That means dinitrochlorobenzene has only activated the nucleus. Eventually, this has this is plus now. So, nitrogen of isoquinoline has been replaced by the nucleophilic nitrogen of the reactant. That is not all. The reaction that we are about to talk about is this one. You have it is a double bonded compound. Now, you can see between, if again we are talking about the Diels-Alder kind of reaction, you have an olefin, of here, it is a methoxyolefin. Methoxyolefin means the electron electronically activated because of the lone pair of the oxygen. So, it is electron rich dinophile, and in this case this one is the dinophile, the pyridine nucleus is dinophile. So, this reaction that would take place and give the product, just 1 minute, okay. This one, and you have this side chain, then you have this pyridine nucleus and oxygen, this, and probably this one. So, what is the lesson? The lesson is that this olefin component reacts, and even though that means even with a single nitrogen you can expect a Diels order reaction provided it is sufficiently activated by quaternization, and this and then it undergoes cycloaddition, and eventually you can go on, and there are plenty of examples. Maybe what I will do, then you group of 2, any, okay, you choose your own group, okay. You do this homework very quickly. Okay, you give me you send me a PPT or Word file with a chem draw, right? All of you have the chem draw, okay, and just write down the reference. 1983 JAX, page number 6. Okay. Some of you, not all. Okay, I will give you 1, 2, 3 references. So, you just divide among yourself. Okay.